Okay, let me give you the big picture on the short time Fourier transform, and then introduce my final comment on the Gabor and the Stockwell transform. So, as a special case of the short time Fourier transform, I have introduced the Gabor transform, which is an STFT using complex using Gaussian windows. Okay, so and this window is in such a way that the parameter alpha, when alpha tends to 0, you're going to get a very long windows. When alpha is very large, instead you're going to get very short windows. And as an application, we have compute we have considered a chirp signal, which is given by the sum of these two complex exponentials. And we just focus on the Gabor transform of the complex exponential, which is given by this. So if you look at the previous videos, there is the full derivation of the Gabor transform of this complex exponential. And what is nice, the expression is very compact. Then it can be written as in polar form with an amplitude times e to the j a phase. And in particular, if we consider the amplitude, we were able to derive this very nice expression. And you can see that the amplitude of the Gabor transform is basically an exponential. It's still a Gaussian bell, and it is centered at omega equal to b tau, which is basically the local frequency of the chirp signal. Okay, so as time increases, the local frequency become bigger and bigger, as you can see. And let's try to learn more out of this formula. Okay. This looks like a complex exponential, as I showed before. Indeed, Ag of omega tau. It looks like something like exponential of xp of minus omega naught square divided by 2 sigma square. And this is what? This is basically a Gaussian bell that it is centered at omega naught, and the inflection points are at omega naught plus sigma and omega naught minus sigma. Okay, this is pretty standard from, for example, probability and statistics. Okay. So I don't care about the amplitude in this case, okay? So we just worry about the width, which is given by this quantity. So now, if we compare these two quantities, so we can rewrite we can learn from that Ag of omega tau. We can basically rewrite it in this form: square root of pi divided alpha square plus b square divided by 1/4 exponent of minus. So here now I have the 4, so I'm gonna borrow a 2 from it, and then on the numerator I'm gonna define omega minus 2 beta tau, which I already have it, which is this. And the denominator, I'm going to write it as alpha square plus b square. And then I'm going to bring the alpha down here. And I have a 2 left over from here. Okay? So this is basically the width of our signal, of the Gabor transform. This is the mean value, omega naught. And this is the variance, basically sigma square. Okay, so we have that when omega is equal to 2 beta tau, you get the maximum value of this exponential because it is centered at omega naught. And then as you move away from 2 beta tau, no, there is a spread given by this quantity sigma square, okay? So if I try to plot this function, the amplitude, as a function of tau and omega, so the maximum is attained on omega equal to beta tau, okay? And then I have, at any given tau, there will be a spread given by a Gaussian distribution, and this spread will be easy to compute. No, we already have it. Actually, it's vertical. Sigma Gabor is equal to the square root of this guy. So it's going to be square root of 2 times square root of alpha square plus beta square divided by alpha. Okay? So now let's study the variation of this diagram with respect to alpha. Okay? Now, when alpha, because now I would like, let's understand more in details. Let's understand better what is how this spread, how the spread with respect to 2 beta tau changes with alpha. Indeed, I can rewrite sigma g square as 2 times alpha plus beta square divided by alpha. Okay? And if we plot this this expression as a function of alpha, here I'm going to do sigma g square, we learn something basically. There is a dependence on a linear dependence on alpha, and then there is a decay with 1 over alpha. So what's going to happen? We get something like this. Okay? So there is an optimal alpha, which can be easily computed by taking the derivative of this function with respect to alpha. And it is pretty straightforward to show that this alpha basically is equal to b. Indeed, is the minimal value that you can get, okay? So you just take the derivative and set it equal to 0. Actually, let me do it here. So the sigma g square with respect to alpha is equal to basically 2 minus 2 beta divided by alpha square equal to 0. And then you can see that 2 and 2 simplify, and then I get alpha square minus beta square equal to 0. So alpha equal plus minus beta. And I only take the positive root. Now, of course, so you see that when alpha is very small, the spread is very, very large, and then it will tend to infinity when alpha tends to 0. And that's what does it mean? It means that this bandwidth becomes larger and larger. So this is when alpha is very, very, very small. So indeed, when alpha is very, very, very small, you can see that I tend, when alpha, especially when alpha tends to 0, I basically get 1. So we lose localization in time. We cannot anymore distinguish the local frequencies, okay? Because when alpha is very, very small, this corresponds to a very long window. And this is equivalent to take the full short time to do the full Fourier transform. Okay, so this is alpha very small, and so it will be when the window is very large, and so I see all the frequencies in my signal, and so that's why this the spread around the 2 beta tau become larger and larger. And I cannot anymore distinguish all the single frequencies, okay? Because now what's going to happen, I have a signal. Maybe let me redo it again. So the important things to remember here is, so here we have tau and omega. So the main line omega equal 2 beta tau. And then we have a spread, basically. We have the spread in the vertical direction. So when, the spread is governed by this equation, 2, which multiply alpha plus beta squared divided by alpha. And that's what we need, okay? So this is enough. So when we plot this quantity, sigma g squared with respect to alpha, there is a linear variation, there is a decay, and then you're gonna get this at b. So when alpha is very small, what's gonna happen is that we have a large spread basically around the frequencies, okay? Around the mean value. This for alpha very small. Instead, if alpha is very large, everything gets more localized. This is now when alpha around b. Okay? However, if alpha is greater than b, then things, the spread it become again larger, but not as bad as it will tend to infinity, but very slow as alpha is growing. So we get something in the middle. Okay, so this is when alpha is greater than b. So now it's very strange, it's right? Because let's try to understand this behavior, okay? When alpha is very small, the Gaussian window becomes, let me remind you the Gaussian window. That's when alpha tends to 0, okay? So Wt equal e to the minus alpha t squared, okay? Now what's going to happen is that because our signal is the following, okay? So of course here I have to when the window is very large, when alpha is very small, you see that the spread almost become infinite. Okay, so we lose completely we cannot anymore identify the main local frequencies. Okay, because the spread is huge. And why? Because now the window is very large. And you see that this window now, especially as time goes for large time, it sees a lot of frequencies, because there is, in this range, the frequency changes a lot, and so it cannot anymore, it's not able anymore to distinguish the change in frequency that occur as time goes on. Of course, there is a minimal width. There is an optimal length of the window that is going to give me the best localization in frequency, because, and this corresponds when alpha is equal to b, which is able to still give the best be able to detect all the changes in frequencies that occur as time goes on. But then what happens, even if the window is too small, if the window is too small, and this happens when alpha is very, 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 very large, then it will be even very the spread tend to increase, okay? Because then it will be even more difficult to, now that the window is so small that it's not easy to, is not able to recognize the changes in frequency that occur with large times, as the time increases. So you can see that even with the Gabor transform, the choice of the window is very important, and you still have to battle with the uncertainty principle. Delta t times delta omega is equal to constant. So here you see now now what is the alternative here? The alternative is to use the idea of Stockwell, who come up with a very simple idea. And as a geophysical application, we are more interested in the low frequency component. So we want to make sure that in geophysics, low frequency components are important. Low frequency components are the one that we want to identify the most, okay? And so, ideally, in order to identify the low frequency component, we would like to use a long window. Is right? And instead, for the high frequency component, we can choose a short window, so that we can detect when they change, when change in high frequency occur in time. So what we would like to have is, for example, now we can choose a longer window that will give me good frequency localization. But then we lose so we're going to get a good frequency localization. And then on the high frequency, if we use a short window, we're going to get a good time localization. And this is a good compromise that can be easily attained by simply choosing a window Wt of this form, minus beta omega square t square. So it's still an exponential window, but now the amplitude, the parameter here, which previously was alpha, now depend upon the frequency. And you see, when the omega is very small, low frequency, we have a very long window. This is for omega very, very, very small. Instead, when omega is very, very large, the window is very short. Okay? This is for omega very, 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 very large. And this is very, very, very small. Okay? And with this simple trick, we basically get what is called the Stockwell transform. Very simple idea. The Stockwell transform is given by xs of omega tau is equal to the integral between minus infinity and infinity of x of t e to the minus beta square. Beta is a parameter that we can tune, e to the minus j omega t in delta t. And this is the famous Stockwell transform. which is going to give me good frequency localization at the low frequency and good time localization at the high frequencies, just by, by simply using a parameter here that is frequency dependent. What is interesting that the formula for the formula for the Gabor, we can use the formula of the Gabor transform. So if we add a signal x of t equal e to the j bt square, we saw that the amplitude, the Gabor, we saw that the amplitude of the Gabor transform was square root of pi divided alpha square plus b square a quarter exponential of minus 1/2 omega minus 2 beta squared divided 2 alpha square plus b square divided by alpha. That was the amplitude of the Gabor transform, okay? So the equivalent, by simply setting alpha equal beta omega square, we get the Stockwell transform very immediately, okay? So the Stockwell transform, the amplitude of the Stockwell transform is square root pi divided beta square omega to the fourth plus b square a quarter exponential of minus 1/2 omega minus 2 beta tau squared divided 2, which multiply 1 over alpha, which become 1 over beta omega square, plus, no, sorry, I made a mistake. So here is beta square alpha plus beta square divided beta square. So you see that now we get dependence on the frequency. Okay, in particular, the variance, the spread around the mean, which depend upon omega and tau, is equal to, remember now, is equal to twice alpha plus beta squared divided by alpha. So it's equal to 2, which multiply beta omega square plus b square divided by beta omega square. And again, what we see that now we get a spread that depends upon the frequency. In particular, so let's understand how is the spread. And so we see it here. So if I plot this guy as a function of omega square, I get the linearity and then the hyperbola here. So the behavior is going to be this, with a minimum that occur at b. Okay, b over here, if I'm plotting, let's assume I'm plotting beta omega square. Okay, so we can see that